Y14 Faraday's law and RL circuit. We consider magnetic flux. In the presence of magnetic field, we introduce a surface element, d sigma, represented by a vector whose magnitude is the area of this surface element, and n hat is a unit vector perpendicular to the surface. You should be careful whether you choose this direction or that direction, that is opposite. Usually, we choose a single direction. If in case you choose a closed surface, the normal vector is always from inside to outside. So magnetic field flux phi m is the integral over a kind of surface, magnetic field and surface differential vector scalar product integrated over this surface. When it is a constant magnetic field is passing through an area, then it is simply strength of the magnetic field multiplied by area. Be careful, if it is parallel to the normal vector is parallel to the magnetic field, in that case BA. If it's opposite, it should be minus BA. Faraday's law of induction states that we evaluate phi m over a surface surrounded by a closed path C if this magnetic flux changes with respect to time, the time derivative multiplied by the negative sign is the potential difference after a round trip along this path along the counterclockwise direction. Change in potential, same place, same point. If you return to the same point, the potential changes. It's very important. It is something like you have a battery. You have a battery in a circuit. When you return, then potential decreases, and then when we cross the opposite direction, this is negative and positive. When you start here, return to the same point, even though you have a decreasing potential, suddenly when you pass through a battery, your potential goes up. Something like that. The change in the potential is not a sudden one, but continuous. Okay. So potential can be evaluated by integrating over a path about what? Electric field and displacement scalar product. So this one is identical to this. We express this time derivative, negative time derivative, and phi m is the magnetic field flux, magnetic field surface vector integrated over the surface. Now we know, use the Stokes theorem, replace this closed path line integral in terms of curl E and scalar product with the surface. Now this surface, the same, move this one to the left-hand side. If you insert this total time derivative, it becomes the partial time derivative of the magnetic field because you do not take the time derivative of the surface. So it becomes a partial time derivative. Move to the left-hand side to replace this negative sign with the positive sign. Now we can shrink this size of the surface arbitrarily small, then this integrand is factored out because it becomes a constant. S goes to 0. It is 0 at every time, therefore this integrand vanishes. So if it is 0, then it is written in this form. This Faraday's law for the integral form and differential form. The negative sign in here is called Lenz's law that opposes the change in the magnetic field. If North Pole is coming in, flux through this direction increases. The direction of induced electric field due to the changing magnetic flux is to oppose the opposite direction, oppose the change in the magnetic flux. Therefore, to prohibit the increment of the flux along this direction, it creates the magnetic field like that. We know the magnetic field is generated only if the induced current is rotating like that. The other figure is opposite case. We have a magnetic field, constant magnetic field, and we would like to see what's happening. We are moving this circuit to this direction. When it is moving with this direction, the flux passing through this yellow area, because the area of this yellow region decreases. So phi decreases. The Lenz's law states that it would like to increase the lost amount of the magnetic flux. How can I do? Create the current inside the loop, then it will produce the magnetic field that fill the gap. When the current flows, and if there is a resistance of this circuit, current I is E over R, and E can be computed with what? Minus phi m dot. We can determine the change of the flux and put the negative sign on it, and you determine the electric potential. This is not an electrostatic potential. This is due to the changing magnetic field, so induced electric potential, and that creates the current And induced current satisfies this relation. Why? This is the force this current flows. Current I flows in the magnetic field. You feel the Lorentz force, that is Q V cross B, or I current vector L vector IL length ILB. ILB is nothing but the QVB. The force is along this direction, backward to your applied external force. Y, V, B, V cross B. It is opposite direction. So your force and magnetic force, they make an equilibrium to keep the velocity of this current loop constant. In that case, you have a work, your force and velocity that creates F dot V. They are parallel. Your force, your external force, and the velocity, they are parallel. So it is a positive. That means your power is a positive. According to work kinetic energy theorem, you have done some work on a system, then the total mechanical energy must be, no, kinetic energy must be increased. However, kinetic energy is constant because the velocity is constant. What's wrong? The supplied mechanical work is lost by the Joule heat, that is I squared R. So your energy supply is consumed by the resistor inside the loop. And the amount is identical to the mechanical. So supplied work is mechanical work, and that work is lost per unit time by the Joule heat. Induced electric field. We recall this Faraday's law. Magnetic field changes. So flux passing through some region changes. Put the negative sign on it. Then you will find the potential difference around a single turn of a closed path. First of all, if you choose this small radius, this is common. So time derivative of magnetic field and negative sign is factored out. Then this area is pi r squared and total area is pi capital R squared. You will find these two magnitudes are different. So this one is bigger, this one is smaller. So the potential difference around the turn should be greater for this one. But if you are outside, because there is no B, this one and this one should have the same amount because magnetic field flux is isolated in this region. In such a manner, we can compute the electric field. This is electric field integral over a closed path, and use this one to find out here electric field magnitude What's wrong? It is r squared, this integral, 2 pi r. Okay, so we divide this 1 by 2 pi r, 2 pi r. Then pi cancels, factor of 2 in the denominator. It becomes r squared over r is r. So capital R squared over r. This is 1 over r. So from outside, the strength of the electric field change along this line decreases. Okay. Magnetic vector potential. Non-existence of the magnetic monopole, we know this. In the case of electric field, it is rho over epsilon 0. It is a monopole charge distribution density per unit volume. There is no monopole, so with divergence B is 0. As a result, divergence B is 0. B should be a curl of a certain vector. Why? In the previous class, or we know A triple scalar product, A dot A cross B. This is 0. AA parallel. Triple scalar product is a kind of determinant. Gradient operator, scalar product, gradient of a car of a vector field. It is always a 0, just like a triple scalar product. So if there is a magnetic field, there is, we call this one magnetic vector potential. Curl A always exists, and that is identical to B. If we can write B equals curl A, then why don't we make use of this, replace this 1 by curl A, and move this 1 to the left-hand side. Then I can factor this curl, and the remaining piece is the sum of electric field and the time derivative of a magnetic vector potential. And curl something is a 0. You know, this is conservative. Any central force satisfies curl something 0. So we were able to make use of total mechanical energy conservation for that case. So this one can be identified with a gradient of something. Physical sense is negative sign. Force is minus gradient potential energy. As a result, electric field is, we know this one very well. This is an electrostatic case. We have time derivative of vector field. Time derivative, this is static, time independent. And this time derivative says time dependent. Electric field has two components. One component is a time-independent charge distribution will generate the electric field. That is the electrostatic field. However, we have another electric field that is generated by the changing magnetic field. Changing is dynamic. It is not static anymore. Two components must be considered to reproduce all components of the electric field. We already have noticed that electricity and magnetism are not separable. They are combined. There should be a single theory. That is the Einstein's relativity. Inductor, a circuit, current I, magnetic flux, that magnetic flux is proportional to current I. Then the ratio flux divided by current is called inductance L. If there are a number of turns, that inductance increases by a factor of turns. The unit for the inductance is Henry. Substitute to the Faraday's law, phi equals Li. Inductance multiplied by current is substituted. Inductance may vary if we deform a circuit, but if a circuit's geometry is fixed, then L can be treated as a constant. So time derivative is applied to the current only if the circuit is stationary. Inductance of the solenoid, we know the solenoid and we know how to compute the magnetic field inside the solenoid, where small n is number of turns divided by the length of the solenoid. Using this, we know how to compute the magnetic field inside the solenoid. Number of turns is multiplied to the single flux passing through a closed circuit. We can find the inductance multiplied by current. The inductance multiplied by current is a total flux, and total flux is, in the case of solenoid, we use constant magnetic field, cross-sectional area a number of turns. Why don't we replace this one by n times L, because the small n is number of turns divided by length. This one is, using this result, we can replace this one. B is here, mu 0, we have n squared, I single, A length. What is AL? A times length. Volume inside the solenoid. This is a volume. So in here we have I can be removed. We have mu 0 n squared, where n is the total number of turns divided by the length of the solenoid, multiplied by volume is the inductance. So you had better remember this formula. Self-induction in a circuit, we have L can always expressed in terms of magnetic flux, L times I. Use this, substitute to the Faraday's law, we can find the potential difference between the two terminals of an inductor. That is always a minus coming from the Lenz's law, inductance and time derivative of current. If you have serial connection of many inductors, we would like to express this one as a single one. That is equivalent inductance. If they are connected in serial, potential change can be added. Potential change can be added. from the one end to the other end, the potential change can be summed. Each potential change, according to Faraday's law, we can replace this one with this form. In here, current I is invariant. Current I, there is no branch, therefore current I is a constant. So we can make use of a single current. So it should be equivalent to like that. Therefore, we can read off the equivalent inductance from this relation. It is opposite to the case of the capacitor. And in here, we have a parallel connection. Invariant one is E is constant. Now, current is divided into many pieces. The sum of current should be considered. So, current conservation, time derivative, just time derivative of this, and time derivative is E over L. Replace everything over E over L, and E, potential difference is constant. Divide this E out. We end up with the result for the parallel connection. Our L circuit, it is quite similar to our C circuit. Mathematical structure is identical to each other. So I don't have to explain in detail about solving the equation. Let me explain the solution. What's that? At t equals 0, there's 1 minus 1, no current. Aha. If you close the switch, current starts to flow. However, this one prohibits the change in current. Inductor prohibits the change in current. So the current cannot rise very fast. It is growing slowly. In here, the rate of rising this current depends on the time constant for the RL circuit. Decay, if you do not supply any potential difference anymore, without this, if you switch off, the current will stop. However, as long as the circuit is connected, even though there is no battery, this inductor does not allow stop the current suddenly. It decays slowly, depending on the rate of time constant. So in the case, rising up is slow, but suddenly if you remove the battery, it decays like that. This plot is showing this one. Mutual induction is a very fundamental one to make a transformer disconnected two circuits. It produces a magnetic field, but if you have a alternating current, then magnetic field is oscillating. Because of that, magnetic field flux passing through the other circuit changes. According to Faraday's law, we have mutual inductance. Previously, self-inductance. the two disconnected circuits communicate with each other due to the mutual inductance. So that is the very basic idea of a transformer. Finally, we consider magnetic field energy. In RL circuit, potential difference is the sum of the energy loss, potential loss due to the resistor and opposing electric field that opposes the change in the magnetic field flux, so that the change in the current is slowed down due to the L. If you multiply current I, it becomes energy relation per unit time. And that is, what's that? Magnetic field energy. Magnetic field energy. So, just like kinetic energy, magnetic field energy can be defined like that. Its time derivative is this one. We remember how to compute the magnetic field inside the solenoid. Substitute this result to re-express L. In that case, the magnetic energy density is magnetic energy divided by volume. Finally, that value is this. Previously, we have computed the electric field energy density, that is 1/2 epsilon 0 E squared. In the case of oscillating electromagnetic field, these two values are equivalent. We will see later. Now, sum of this electric field energy and magnetic field energy. Remember, epsilon 0 is above, mu 0 is below, and we remember Maxwell noticed that this strange factors product becomes 1 over speed of light. So electromagnetic field, even though electric field and magnetic field are not conservative because of the time varying field, even though each field is not conservative, the sum of the electric field and magnetic field, they are conservative. So our conservation theory is much more generalized version in comparison with the electrostatic case.